Many VMware customers are now transitioning to VMware Cloud Foundation or VCF. They realize they have access to NSX virtual networking, which is a feature they might not have considered earlier on. The goal of this presentation is to explain the benefits of virtual networking in VCF and, of course, to encourage its adoption. In this presentation, we'll start by introducing first what we mean by virtual networking. And at its most basic level, this looks like the overlay model that hardware vendors have been pushing for a while. But we'll see that VCF with virtual networking goes far beyond extending layer 2 with an overlay. It's about delivering an entire virtual networking stack for the application developer. Finally, we'll see that virtual networking is the only way to bring a public cloud-like experience to your data center, and this is, after all, one of the main goals of VCF. Let's start with a simple example. Here, I have two virtual machines running on an ESX host. They are connected to a VDS, a vSphere distributed switch, which operates at layer 2 only. What that means is that this VDS doesn't know what an IP address is. It only switches frame. So, of course, our VMs have an IP address for networking. It's just that those IP addresses are defined in the physical infrastructure, not on the VDS. For example, here, the VMs have an address in network 10.0.0/24. This network is defined on the top-of-rack switch to which the ESX host is attached. In modern data center designs, layer 2 networks are limited to a rack. This is for stability and scalability. Basically, you don't want to extend a spanning tree-based network to the whole data center. So if layer 2 is limited to a rack, it means that an IP subnet in the physical infrastructure cannot span beyond the rack either. As a result, a VM can't move to another rack because its IP address defined by the physical infrastructure wouldn't be valid there. In other words, we are creating silos. Virtual machines are virtual, but their network addresses are physical. They're constrained to a physical location in the data center. This goes against one of the main benefits of virtualization. We want to have the flexibility to run our workloads anywhere in the data center in order to maximize resources. So before I show you how this problem is solved by NSX, let me first mention that as of VCF 9.0, NSX is already available in your standard VCF deployment without any additional configuration. NSX creates virtual networks that are completely independent of the physical infrastructure. For example, here, my VMs are now attached to an arbitrary subnet 100.0.0/24. This subnet does not exist on any of the top-of-rack switches. The virtual networks created by NSX can span the whole data center across rack. So, how do those virtual networks actually work, as they don't exist in the physical infrastructure? NSX configures each ESX host with tunnel endpoints, or TEPs. These TEPs are assigned IP addresses in the physical networks defined by the top-of-rack switches. You can see the first ESX on the left has a TEP with an IP address in rack 1 and so on. If you're familiar with vSphere, you can think of TEPs as just another kind of VM kernel interface. It's the same kind as what is used for management, vSAN, or vMotion. Between those TEPs, NSX establishes tunnels that interconnect the ESX host. So when two virtual machines on the same virtual network but running on different ESX hosts need to communicate, their traffic is encapsulated in an IP tunnel between the TEP of those hosts. This overlay tunnel is tagged with a virtual network identifier, VNI, which is equivalent to a VLAN ID in traditional VLAN networking. And of course, virtual machines can be moved freely from one host to another. NSX automatically manages the necessary tunnels behind the scenes without any user intervention. This gives us full mobility across the entire data center, breaking down silos and enabling workloads to be distributed optimally across the physical infrastructure. So, what are the benefits of virtual networking at that stage? We just said that it enables virtual machine mobility across the data center, eliminating silos and improving the utilization of the physical infrastructure. It can also extend layer 2 networks between data centers. There is no need for a dedicated L2 extension technology. VCF virtual networks can span subnets and connect multiple data center locations. It's great, but it's also something your hardware vendors has been pitching to you for 15 years at least. So let me put what I call the hardware vendor solution side by side with NSX virtual networking. The hardware vendor solutions I'm referring to here are VXLAN or EVPN with VXLAN or even Cisco proprietary ACI. The difference? Those tunnels we talked about. In the hardware vendor model, they run between top-of-rack switches, the hardware devices. With NSX, they run directly between the virtual machines. So note that in both cases we're running VCF, but with the hardware vendor model, the hosts are sending VLAN traffic to the top-of-rack switches. Then the top-of-rack switches map those VLANs to a specific tunnel, a specific VNI. When using VCF with NSX virtual networking, the VM itself is directly connected to the VNI. There is no VLAN to VNI mapping needed on the physical switches. So is that the only difference? And more importantly, does this difference matter? So let's compare the configuration steps for both approaches. Suppose that we want to connect two virtual machines to the same network, so we're in a layer 2 only networking scenario. With the hardware vendor solution, the ESX hosts still operate with VLANs. So we first need to create a VLAN X for them on each rack. Then we create a VNI Y that will extend this VLAN X between the top-of-rack switches, and of course we need to map VLAN X to VNI 1 for this to happen. So this covers the configuration on the network side. On the host side, we still need to create a distributed port group, a DVPG, that is backed by VLAN X, and then only can we attach the VMs. With VCF virtual networking, the process is much simpler. Just create a virtual network that we'll call a subnet here, and attach the VMs to it. With VCF virtual networking, there is no physical switch configuration at all. So just with layer 2 networking, you can start to guess the difference I want to highlight. But NSX goes far beyond layer 2. On the top of this end-to-end virtual layer 2, NSX builds a complete networking stack. And because this layer 2 fabric is independent of the physical infrastructure, the entire stack is also independent of the physical network. This means that we can instantiate a full range of network services entirely in software. Switching and routing, load balancing, VPN, NAT, DHCP, and other advanced services that I'm not showing in this diagram. All of this is deployed in a fully virtualized way, decoupled from the physical network constraints. Even better, these services can be configured together via API. NSX uses an intent-based API model, so you describe the desired state of your network, and NSX realizes it in the virtual infrastructure. This can often be done with a single API call, actually. So let's build on our previous example. This time we're going to deploy a 2-tier application, a very simple lab example with 4 virtual machines connected to 2 different networks, a front-end web tier, and an application back-end network. The application is secured by a firewall. I'm just adding random services here. The web tier is fronted by a load balancer. We also want to expose the application to the internet. And finally, suppose we have some remote locations that need VPN services. So let's build this application with the hardware vendor model. The first step is to configure the virtual networks. This is a layer 2 setup that we discussed earlier. This requires configuration both in the physical network and on the VDS side. After this configuration, the web network and the app networks are created. Next, we need to configure all the services, routing, load balancing, firewall, VPN, etc. That's where the complexity creeps in, as the configuration involves multiple teams. First, we're configuring different types of hardware, router, load balancer, firewall. Each of those appliances has a different configuration point and a different configuration model. This is a vendor-specific, sometimes even software version-specific. And your network might even have multiple vendors for the same kind of appliance. Then you need to steer traffic through the right appliances. Take the firewall, for example. If the relevant traffic doesn't flow through it, the firewall provides no protection. Directing the traffic appropriately is a very difficult task, and configuring this at scale is error-prone. Automation is difficult for this scenario because it requires cooperation between different teams and different configuration models. It's not impossible though, so even if you manage to automate this complex process across vendors and teams, it's still fundamentally not the same as virtualization. Again, consider the firewall. Suppose a firewall appliance supports 100 gigs worth of traffic. When this limit is reached, you must physically deploy another firewall and then adapt your automation and configuration models to integrate the new device. Just think about that. If you purchase additional firewall capacity on a public cloud, do you think this triggers a ticket for an operator to physically deploy a new firewall appliance in a rack? Of course not. The capacity in the cloud is virtualized, scalable, and elastic by design. And the only way to achieve the same on-premises is via VCF with NSX virtual networking, because all the network functions are virtualized. There is no appliance, basically. The deployment of our two-tier application can be achieved with just one or few API calls. There is no change required in the physical infrastructure. This is true network virtualization. Thanks to network virtualization, our customers report dramatic reduction in deployment time. Without virtual networking, due to the cross-team interaction and the ticket-based processes, deploying a new application can take weeks. With network virtualization, the same deployment can sometimes be completed in just seconds. All of this is possible because network virtualization, together with, of course, compute storage, all three provided by VCF, by the way, enables the automation of every aspect of application development. This also powers advanced automation platforms like VCF Automation, which is also included in VCF, which provides a complete framework for templating and automating the entire lifecycle of applications. Another key use case is disaster recovery. With network virtualization, the entire networking environment from a failed site can be replicated instantly to a recovery site, dramatically reducing application recovery times. And beyond the scope of this presentation, network virtualization also simplifies the management of policies and interconnections across multiple sites, ensuring consistency at scale. But what if I don't need virtualization? I have a very small data center, it's very static, we don't deploy new application very often, etc., etc. A common misconception when adopting VCF is that you need to migrate your entire environment from VLAN-backed networking to NSX. It's a myth. Think of virtual networking as an added feature that is available, not a replacement for your existing deployment model. When you onboard VCF with virtual networking, your current applications keep running as they do today. And the best part, you can continue with your existing networking model while using virtual networking at the same time. For example, only deploy your new workloads on virtual networks. You can get the benefits of virtual networking without any disruption or mandatory migration. So let's wrap up. With NSX virtual networking, combined with compute and storage virtualization, VCF delivers a true cloud-like experience on premises. We eliminate silos and enable full VM mobility across racks and sites. We've seen that networking becomes simpler, no coordination with hardware team or physical switch configuration, and more powerful with a complete set of services, all virtualized and API-driven. Most importantly, this model scales like the cloud. It's elastic, intent-based, and automated. So what took weeks to deploy now takes just seconds. And that's a promise of VCF with virtual networking.